Okay. Okay, hi everyone. Happy to be here in Tokyo to present some work that I've been doing. My name is Valerio. I'm a security engineer at Trail of Bits. And today we're going to talk about fuzzing, Go application especially, and how we have been working on modifying the Go compiler to detect more bugs while doing fuzzing. First, I would like to know who here in the room has ever done fuzzing on Go applications? Is there anyone here that has been doing some fuzzing in Go? Okay, one person? Okay, so I will start with a little story. So before joining Trail of Bits, I was doing a lot of Rust security and reviewing a lot of Rust application and doing a lot of fuzzing in Rust. And when I joined Trail of Bits, I did way more Go fuzzing and trying to find bugs in Go applications. And while doing my fuzzing campaigns, I realized that integer overflow could not be detected in Go, while it's possible in Rust. So that was a big problem, because then it means that when we were fuzzing some Go application, we could just not detect those bugs. So it was a big problem for me. So I started to wonder, why isn't it possible? Why can't we do it in Rust and not in Go? So the current behavior of the Go compiler is that when you have an application that is compiled in debug mode, if there is an integer overflow, the application will just panic, which is great, because then you can have an integer overflow and then the application will stop and you can clearly see when there is a bug. However, in Go that is not possible. There is no feature, there is no flag on the CLI to stop the application and tell the developer that there is an integer overflow. It will just wrap around. So for example, if you have a number and you do an addition and the number goes very large and it overflows the memory that has been allocated for this, it will just go at the beginning and wrap around. So we can imagine that there is a lot of security issues that might come with it, right? For example, let's say if you have a nonce in your application, the nonce is supposed to increment every time. If at some point the nonce resets to 0, that's a big problem, because you can do signatures replay, for example. So people doing Go security before were trying to catch those integer overflow bugs with static analysis. The problem with static analysis is that there is a lot of false positives. Basically, a simple static analysis tool, we try to just see there is, for example, a plus or a minus in the code base, and then tell the developer or the security auditor, hey, there is a plus or minus here. Maybe there is an integer overflow, but who knows, maybe before the developer made some code so that it checks the bounds of the variable. So that's very verbose and not very deterministic, let's say. So before I start to explain how we did it, I would like first to show how it looks like. So here you can see a simple Go program. It's just A equal 120, B 20. You do R equal A plus B, and then you run it with Go, the native Go compiler, and with the fork that we did. Here you can see that it wraps around, so 120 plus 20 equal minus 116, which is not what we want, of course, and this can create many logic bugs. But with the tool that we made, it will just panic, and then you can see when you run the application or when you do Go fuzzing that there was an integer overflow, and maybe treat it as a security vulnerability. So that's how it looks like. So before going more in depth, I would like to give a high-level overview how we did it, basically. So first, we forked the Go toolchain, and then we try to see where in the Go toolchain it will be the best place to modify the toolchain. Where since we want to edit the compiler, where should we insert our security checks if there is an overflow or not? So it was in the intermediate representation endlink. So then we just modified it. We added an overflow detector that we'll see after for each mathematical operation, like for example when there is a minus, when there is a plus, multiplication, division. And then we made it so that it inserts a panic when the integer overflow is detected. So first, I mentioned here spotted where IR and link is in the code base? The answer of this is SSA. So let's go back a bit on how does a compiler works in a high-level perspective. First, you have your source code, then you have a bunch of scanners and parsers that will parse your application, the source code of your application. This will build an abstract syntax tree, which is the AST. Then it will go into the SSA, and then it will go into the machine code, let's say your binary, your x86 or ARM binary, for example. So the best way that we decided to implement our overflow checks was in the SSA. SSA stands for single static assignment, and that is basically an intermediate representation that is in Go, but it's also in Rust. In many languages they have SSA. Basically, SSA is when you try to have, you take your source code and you make one variable each time. So for example, if your application contains A equal A plus 1, then the SSA of this would be B equal A plus 1, and then C and D. Basically, you try to create as many variables as you can, and that's used for compilers for optimizations, for example. So in a simple explanation, SSA is just basically your source code, but with many variables in between to have more details in a more granular application. All right, so let's take a look how SSA looks like in Go. For example, for an addition, you will have this, v1 equal, so let's say you have just A plus B in your Go source code. You will have O add A and B in Go, but with our tool, you will have also O add A and B, and then you will have if overflow detected, then call a runtime panic, stop the application. That's our work. So now the question is, what is this overflow detected and how does that work? So let's take a look with how it works with signed integers, for example. So let's say int 8, int 16, int 32, for example. Well, there are three scenarios. The first scenario is if A and B are negative, like we had in, I think in the example before. Second scenario is if A and B are, one of them is positive, and then the second one is if A and B are positive. So just for simplicity, of course, we won't go through any of them, we don't need to. Just maybe let's have a look at the case where A and B are negative. Let's say you have A and B minus 120. If you do this in Go, you will have 16, which is an underflow, but we want actually this. And the check that we need to do is the result of this bigger than this or this? If this is bigger, then that's an integer overflow. And that's the kind of check that we can do in the SSA in order to detect those bugs. So, of course, you can detect integer overflows with this, but if you think a little bit further, you can also detect other bugs. What about, for example, unsafe cast? Let's say you have a unsigned integer on 16 bits, that is 256, and then you do a cast to a uint 8. It truncates to 0, that might be a bug that you want to detect because that might not be the behavior that you were suspecting. Then you can just do the same and add some checks to see if the result that you will have fits in the size of your integer. We did it in Go Panicking, our tool, but that's disabled by default. All right, so let's take a look, for example, at how it looks like if you compile your binary with this with Go Panicking and you put it into Ghidra or like any binary disassembler. Well, you can see here, for example, if you have a plus, then you do the addition, val plus SOR21, so A plus B, and then after this, you do a bunch of checks. You check, for example, if A and B are negatives, but the result is a bigger number than A or B, then you panic. Or if A and B are positive, and the result is smaller, then you also panic. So that's how it looks like in your binary. Of course, this tool was made especially for fuzzing, and you might not use this for your deployed code because maybe you don't want to have some panics in your application if you use it on production, obviously. All right, so this comes with a little bit of issues, which are false positives. So when I'm talking about false positives, it's not necessarily about the fact that maybe there was an integer overflow that was not. This doesn't happen, this always works. But maybe you have an integer overflow that was intentional. Maybe the developer actually wanted the integer overflow. And in that case, we created two ways to tackle these issues. The first one, you can just add a comment here, and then when the compiler will detect these comments next to your mathematical operation, it will just not perform the checks. Another thing that we did is that we did the source location filtering. So, for example, there is a lot of libraries, cryptographic libraries, randomness libraries in Go that relies on integer overflows, and in that case, the further or like the Go compiler will catch it, but we know it's false positive because this is the intentional behavior. Then in that case, we just hard-coded a bunch of files where we say to the compiler, hey, if you detect a bug here, it's not an issue, it's okay. All right, so we tried to test this tool on some project, and we found a bug in the Cosmos SDK. So for those who are not, I'm mainly doing blockchain audits, and Cosmos SDK is a blockchain SDK to create blockchains. And I was doing some fuzzing with the tool, Go Panikind, to detect maybe those bugs. And I was fuzzing the RPC, and it found a bug here. So for example, the bug was that when you have a page where, let's say, you want a list of validators. For those who are not aware of blockchain, validators is just the machine connected to the network. Let's say you want to list all the validators, you can have an offset and a limit. For example, I just want like the 100, the first 100, I just want the 100 results of the machine connected, and after like 10 of them, for example. The problem here is that this was unsafe. This overflow was not detected before, and so we could catch the bugs before, and we reported it, and it got fixed. All right, so when I did this tool, I realized that actually this could be just the first step, because the Go fuzzing ecosystem is really poor compared to the Rust one, and I realized that maybe I could bring some of my knowledge about how fuzzing Rust works and doing it in Go in one tool, like all in one tool, and this is what I did. So what we saw now is just the first feature, integer overflow and truncation issues detection. When I made the call for proposal for SECCON, back then it was some months ago, this was not in my head, but since then I started to work on that tool and to expand more. And you can have a look at the GitHub here, it's here. So now I just presented the feature one, but I created a tool where there is a bunch of other features that is really useful for people fuzzing Go application and maybe catching bugs in Go. So the installation of the tool is really easy. It's just like the Go compiler. Clone it, go to the source directory, make.bash, export the Go root, and then it works the same way as the Go compiler. It's exactly the same commands. And yeah, that's it. Thank you very much, everyone.
Okay, thank you very much. Is there any question from audiences? No, thank you very much for your interesting presentation. And I'm a bit curious about the fuzzing ecosystem in Go language. You say it's very poor, but okay. There's two questions. Sorry. The one question is, did you find any other vulnerabilities, not especially in integer overflow, but other kinds of overflow by fuzzing to the Go application?
No. However, as I said, there was new features, and I recently found some vulnerabilities in other applications, but not integer overflows, just other vulnerabilities. Because the tool now has way more features and adding those features helps to find these bugs.
Okay. Yeah. The reason why I asked that question is how the fuzzing is how effective for Go applications. Is it same as other languages, or especially for Go language, it's less effective or not? Because I'm curious that why the fuzzing ecosystem is so poor in Go languages.
That's a really, really great question. I don't know. I think it's because Rust is way more security oriented. We know that Rust was made for security to avoid many issues, memory safety issues, especially. Go is a bit less security oriented. Also, for the fun anecdote, what I did here is not new. Many people submitted some issues and some pull requests into the Go compiler to implement this, but the Go community always said, no, we don't want this, we don't need this.
Wow.
Yeah, so I did it as a standalone because for my job and my hobby, I really need it. But many people thought about this before, because the community always refused it.
Okay, thank you. Yeah, I think that Go is one of the popular language, but it's not so much of the ecosystem for fuzzing in Go language is very, very interesting for me. So thank you very much for sharing.
Thank you very much.
Thank you very much. So yeah, big